Okay. So we plot this from 0 to 1 we have 2. So 0 to 1 we have 2. So another value we will repeat this pattern. So for the same interval x plus 2. So we should have another one here like this, and then after this line we need to have this one also here. So it is repeating until, so they want to until -3 to 3, so it's repeating. Okay, Fourier coefficient. So for the Fourier coefficient we need to have a naught and then fx. So what is our fx? So we have fx, we have two fx here, x plus 4. So x plus 4, and then we have another function which is 2. So we have 2 here. Okay, we have 2. So that's why we add this. So we add these two, and then we find we put the range of this periodic function. So then we can calculate this. This is the value of the a naught. Also happen to the fx for alpha n, so, for a n. So fx kita x plus 4, and then we have this value, and then we have another value here, but where is L over L here? Where is over L here? Over L here is covered by what? This is over L, so L, what is our L? 0 minus minus 1. So we have 1. But then put here L as a 1. Here is, you should put L equals to 1. Alright. So because this range this is 0 minus 1. This is 1 minus 0, so also 1 here. Alright, so we complete, and then we integrate these two function. Okay, integrate these two function and also these two function. So these two function we need to integrate. We have this. Okay, we have this, and then we put the finite integral. Finite integral here, also the finite integral, we put the value here, and then once we put the value, so this is for x value. So we put this value into the x. So that's why you can see here there is no x here. So we left with this. So either this give a value sign 0. So sign 0 we will get. Okay, sign 0 we will get 0 or 1. 0 or 1. Okay, sign 0, you will get 0. So that's why you can see here That's why you can see here 0. This is everything times 0, so we get 0. So this is 0 because of sign 0 equals to 0. Okay, cos 0, so you put here cos 0. So you put here cos 0, you will get cos 0. 1. You get 1. Cos 0, you will get 1. Okay. That's why we will have here, we will have 1 here. And then n pi square here, we still maintain the pi square. Alright. So, what we'll have, we will have negative. Okay. We know that this is cos 0 equals to 1. So how about n pi here? So if we put n pi here, so cos, again cos 0, okay, times okay, times pi times n. Times n, maybe as long as n is integer, so maybe we can put 6. So they also will give 1 because the maximum value for cos is 1. That's why actually enough to put the value of x inside the cos. So that's why here you can see in this function they only give you the left is 1 over n pi square. And then you put negative 1. You put negative 1, there is, we give the different value. So you have this value. And then here is sine 0. Sine 1, okay, you have this value. But sine 0, you get the 0 value here. And then once you deal with this value, what should you have? You will find the value of this in general. So you simplify. After that, you can get this value. And then again here we can simplify, and then we just left with this function. Okay, so now we go to the bn. So we go to the bn. Bn is we use this formula. And then we have difference, also the similar thing, you need integrate, and then you get the function after integration, and then you get this function after integration, and then the finite number here. And then put inside this number here, put inside here, and then after that you can get this value. Okay, this value. And then what you will have, you will simplify this. Okay, this you can simplify, become this. And then from here we can put this as a constant, so we just only left with this. So you get the constant for bn, an, and a naught. So the net is the coefficient are substituted for the Fourier series function formula. So the value that we have, we put inside here in the complete general solution for the coefficient, Fourier coefficient for the Fourier series, right? So there is another example. The example we deal with the constant. And then there is another example here. They deal with the function. So first of all, we sketch. For example, we need to sketch this. We need to have a point, to at least 2 points. A lot of points may be much better because we can get the more accurate function. So here we can find x. X meaning a linear function. Then we need to sketch until negative 3 pi to 3 pi. And then find for the Fourier series coefficient, meaning you need to find A naught, AN, and BN. To find them, so just as we need to express this equation first, and then this expression delegate as L as a 2 pi for the periodic function here. So for A naught is easy as that, we just deal with the fx and then we integrate, we get this. Okay, for AN we need to deal with cos function and fx, integrate, and then we get this as similar as we do the previous one, and Bn also here. And then for your final also, this the similar thing that we ask to find the coefficients, Fourier coefficient. This is another example you can see and you can try here. So the different here, I think not much. The same thing that they use, they integrate the function, they combine the function, integrate the function, and then you get the Fourier series. Put the all the answer to the Fourier series with a very nice formula, easy to use lah. So we can use this based on the extra information here we can have here. Here we have the Fourier series, and then Fourier series expansion is 1 plus, we eliminate, define this summation. First, meaning they start with 1, so 1 6 over pi, so 1/6 over pi, maybe in front here, because it is 12. And then we have 2/6 over pi, we have here, because we if 1, okay, if 1 here, okay, we discuss a little bit here. Okay, Fourier coefficient here we have fx. Why is this not happen? Okay, fx plus 1, okay, sorry, eraser. One plus summation of from n until 1, 6 over m pi, okay, close bracket, -1 to the power of n minus n minus 1, okay, minus 1 sine nx, okay, sine nx. Sine nx. Nx. Okay, you can see here nx. Right, so what should we do? How we can get this function? Okay, this is we try to expand this. So fx equals to, okay, 1, we just copy. Here we start with, so we know that n is start from integers. We use only integers from 1 to 3 until infinity, very big numbers. So what should we have? We put 1 for the n here, so 6 1 pi, okay, close bracket, okay, open bracket, n1 minus 1, so you will get sine 1 sin nx, and then we have x. Okay, and then close bracket, and then we will get another one term here. We will have plus, okay, open big bracket, so sec 2 pi, close bracket, -1 2 minus 1 sine 2x, close bracket, big bracket. Alright, and then another one, after 2 we put 3 until we get some number that's very big. So we just put this dot as a 3 dot. 3 dot meaning they will continuous no n, without n. Okay, this is 3 dot. Okay, why here we missing for the n equals to 2? So n equals to 2 we missing. No here, because maybe there will be a 0. So why it can become 0? Okay, so we will have, okay, fx equals to 1. Okay, if we can see here, 1 over 6 over pi. Okay, 6 over pi plus 6 over pi bracket -1 -1, we got the negative 2, and then we got sine x, and then plus we have this 6 over 2. Okay, 6 over 2 pi, and then square 1 minus 1, so you will get 0 sine 2x. And then we have another one here. We will have uh, 3. If we put 3 here, so 6 over 3 pi, this will be 3. So -1 -1, we will get -2 sine 3x. Okay, sine 3x. So here anything we will multiply with 0, we got 0. So that's why this for term n equals to 2, they will finish here. No term here. We just have term for this. So we simplify again. Fx equals to 1 minus 12 over pi sine x minus 12 over 3 sine 3x. So this is 3, 1, and this 4. So that's why after you simplify, you will get this. Right. Okay. Bn term are also all 0 since -1 to the power of n minus 1. 1 minus 1 equals to 0. Alright. So if we plot the non-zero term, we get the approximation fx. Let's represent the partial sum of the first n term of this series. The first few term, here we have this. Then we have this s1 equals to this, s2 equals to this, s3 equals to this, s4 equals to this. So s1 is like this, s2 is like this, s3 like this, s4 like this. So our observation as a number term increasing, and the approximate will get closer and closer to original function. So if we put more term inside here, so we will get more accurate, more close to the original function that we want to estimate. Okay, Sn become a larger, Sm seem to be converged to Fs over the interval of this interval. Okay, so next is Fourier series of even and odd function.